Welcome to your first Algebra 2 podcast. Today we're going to talk about the real number system so that we can get some of the notes taken care of so that we can do an activity in class. Real numbers are just basic, very simple, all possible numbers that are out there. And we're going to represent real numbers with the letter R. And it is just really all the numbers that are out there that you can possibly think of. Those are all real numbers. But we can divide real numbers. This real numbers is like an umbrella, and it has different subsets or categories. And we're going to divide it into some categories that are a little bit more manageable. And we're going to start with, I thought it was easier to start with the bottom here and work our way up. So we're going to start with natural numbers. And we're going to let N stand for natural numbers. And basically natural numbers are your counting numbers. 1, 2, 3, 4, 5, ... as high as you can possibly count. Okay, the next step up is going to be whole numbers. And we're going to let W equal our whole numbers. And basically, whole numbers adds 0 to our natural numbers. So other than that, it's very simple. It's just 0, 1, 2, 3, 4, 5, ... up to however high you can count. Basically, on and on and on. There's really no end. Okay, so the next step, we're going to add to those whole numbers, and they're going to become integers. And we're going to let the variable z stand for our integers. And integers are going to take the whole numbers, and they're also going to include negative numbers. So we come from negative infinity up to, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, ... Keeps going on and on. But at this time, now it goes in both directions. It goes in the negative direction and the positive direction. All right, we're going to move up one more step. And we're going to go to rational numbers. And we're going to let Q equal our rational numbers. We already used R for real numbers. And rational numbers now include the fractions and the decimals. But these decimals have to have a pattern or they have to end. So we could say 0.65 is a rational number. It's a decimal that ends. We could say that 0.677777, and it goes on and on and on. That's also a decimal. It doesn't end, but it does have a pattern because it has a continuous 7. We can have fractions, 4/5. We can have 2 7/8. We could have negative numbers, negative 1/3. Okay, so remember, rational functions are basically your integers that are fractions, or I'm saying they're not integers, they're the one step up. Integers have plus and minus, but they're kind of like whole numbers, whereas rational numbers, that gives us our fractions and our decimals. But those decimals have to end or have a pattern. Well, what if they don't end, and what if they don't have a pattern? Well, then we move over to the left to irrational numbers. And we're going to represent that with an I. And one of the most popular, I call it most popular, irrational number is pi. Okay? We round it off to 3.14 when we're doing, or 3.14, and it keeps going on and on. But most of the time we round it off to 3.14. Another irrational number would be the square root of 2, or the square root of 7, or the negative square root of 11. If you can kind of get an idea here with these square roots, any non-perfect, that's supposed to be non, and then non-perfect square root is considered an irrational number. Okay, easy enough. Let's go down to the bottom of this page and let's define some of these. In this case, we want to make sure we read the directions here. We want to name all the sets of numbers to which each number belongs. So I'm going to start with the bottom with natural numbers, and I'm going to work my way up around and make sure and see if it includes that. So we start with 30, and I would say that 30 is a natural number, so we're going to give it an N. That makes it a whole number, so I'll give you a W. Makes it an integer, a Z. It makes it an irrational number. A rational number, I should make sure I say that correctly, with a Q. It is not irrational, but it is a real number. So we have an N, a W, a Z, a Q, and an R. Let's move over to number 2. negative 11. Now, it's not natural, it's not whole because it's negative. So it is an integer. It is a rational number. Oh, that's supposed to be a Q, sorry. Q. It is not irrational, but it is also a real number. Let's look at number 3. Okay, not a natural number, not a whole number, not an integer, but it is a rational number. It is a fraction. So it makes it a Q, and it falls under the real category. Okay, so what I'd like you to do is I'd like you to pause the video, and I'd like you to do numbers 4 through 9, just like what we did with 1, 2, and 3, and then come back and we'll check our answers. So go ahead and pause, and come back and check. Okay, so I'd like you to take a minute here and check your answers. If you need to pause the video in order to check it, that is just fine. If you notice, every single problem should have an R. Because remember, real numbers include all numbers, whether they're irrational, integers, whole, natural numbers, they're all real numbers. So all of them should have an R. All right, if you're not done, go ahead and pause it, check your answers, and I'm going to go ahead and move on to the next page, or to the back of the next page. Okay, so again, we're just going to practice this. This is a little sorting event, and we're just going to now, instead of giving all the categories, we're going to start with the category that they start with. So if we look at 7 for A, we would say that 7 starts with, or we could place it into the category of a natural number. B, it's got a negative there, so we know it's not natural, we know it's not whole. When we look at it, it looks like it's a fraction, but if we simplify that fraction, 36 over 12 is a 3. So that would be negative 3, and that falls into our integer category. C looks like a square root, so we have to look and say, well, the square root of 36 is a perfect square. It'd be the square root of, it would be square root of 36 is 6, and we have a negative there, so it would be negative 6, so that would also fall under our integers category. Pi, hopefully we can recognize that pi is irrational. 6.48 is a decimal, but it does end, so that falls into the rational category. Negative 2 falls into the integer category. Negative 10. Negative 10 is not a perfect square, so it would fall into irrational. 0 is a whole number. I'm going to bring forward here because I don't think I have that done. It's one step up. So what's the difference between natural and whole numbers? Is that 0? I, it's a fraction, so that's going to go into our irrational category. And this last one, but to be a little careful here, we maybe haven't quite learned this, but you did this in Algebra 1, so maybe you remember. We know that the square root of, oops, click my pen. We have 4 over 81. 4 is a perfect square, and so is 81. So we can actually, divide that into 2 square roots. Let me erase my little mistake here. And we would get square root of 4 is 2, and the square root of 81 is 9. So that would break down to a fraction. So we would put this square root of 4 over 81, let's push that up just a little bit, that's going to go in our rational category. We got one more hiding under here, the negative 0.7, and notice that the 0.7, the 7 has a bar over it. That means it repeats. So it looks like it might be one of those irrational numbers, but because it has a pattern to it, we can put it in the rational category. Okay? All right, so there's some questions on the rest of this page. Numbers 1, 2, 3, 4, 5, 6, 7, and 8. I'd like you to go ahead and do those on your own. And you can then bring those answers and we'll go over those tomorrow. We're going to move on to the next page. You can go back and do those after we're done with the video. We're going to just go over a couple properties that you're going to use throughout the year, and just put a name to them. A lot of these properties are things that you've done before, and we just want to go back and put a name to it now that you've moved into Algebra 2. So the first property we're going to talk about is the commutative property for addition or multiplication. This property states that the order of values does not matter. And basically what's that saying? It says that if I take 2 plus 3, that's the same thing as saying 3 plus 2. It doesn't matter the order in which I add numbers, I come up with the same answer. The same thing applies to multiplication. Oops, that should be when I fix that, that should be a 3 times 2. So it doesn't matter whether they take the 2 times the 3 or the 3 times the 2, I get the exact same answer. This does not apply to subtraction or division. Okay, let's talk about the associative property. The associative property for addition and multiplication applies to grouping of values. Basically says that the grouping of values does not matter. I can take 2 plus 3 plus 5, and that's the same thing as saying 2 plus 3 plus 5. I can put my parentheses in a different place, and I still come up with the exact same answer. The same thing as if I decided to multiply those. Doesn't matter the order. And again, this only applies to multiplication or division. I'm sorry, multiplication or addition. Does not apply to subtraction or division. Okay? The identity property for addition or multiplication basically states that our numbers stay the same. And they're a little different for addition and multiplication. So for addition, the identity property says that if I take a number and I add 0 to it, I'm going to keep the same number as started. Multiplication says if I take the number and I multiply it by 1, I'm going to keep the same number that I started with. And we do use that in very simple solving equation problems. Okay, last two properties. Well, I'm sorry, I have 3 properties left. The inverse property. That's when you use opposites to cancel a value. Addition is very straightforward. 8 plus a negative 8, and negative 8 is the opposite of 8, and that's going to give me 0. That would be the inverse property. Multiplication is a little different. We're going to use a fraction to show this one. If I have 4/5 and I multiply it by its opposite, in this case the opposite is referred to as the reciprocal, which would be its flip version, we're going to get the answer 1. If we multiply across the top, multiply across the bottom, we get 20 over 20, which is 1. And remember that this is really called the reciprocal. Okay? And that would be our inverse property. Last property, I'm sorry, I keep saying that, it's the second to last property. The zero product property says multiplying by 0 always equals 0. And we use this when we solve quadratic equations. So if I took 2 times 0, that's going to give me 0. Or maybe I took 0 times, let's say x plus 3, that is also going to give me 0. So anything times 0 is always equal to 0. Here we go. Last property, again, something you're very familiar with. We use it a lot, is the distributive property, and that is really defined as multiplying a value to multiplying a value to an expression inside our parentheses. So for example, we have 2 times x plus 7. If we distribute, we're distributing the 2 to the x and to the 7, and we get 2x plus 14. We multiply those together. If I have a negative, we're going to let the number own the sign in front of it. In both instances here, we're going to take a negative 6 times x, which would be negative 6x, and a negative 6 times a negative 3 is going to give me a positive 18. If you let the number own the sign in front of it, the signs all take care of themselves in the final outcome. Okay, so the only thing I'd like you to kind of go back and make sure you go back and do is numbers 1 through 8 on the previous page, and otherwise we'll go ahead and pick up where we left off tomorrow. Have a great night. See you tomorrow in class.